In this video, I'll be showcasing an overview of my robotic arm project. Here you can see the certain criteria given by Plymouth University, where I am to build, code and control a robotic arm with 2 degrees of freedom, the function of which is to draw a square on a whiteboard. Here you can see a servo motor. The servo motors are the main component we are going to use to move the arm. This is one I have designed in Fusion 360. Here you can see the brown cable is used for ground, the red cable is used for 5 volts of power, and the yellow cable is used for PMW signal. Here you can see the motor clip. This has holes allowing us to screw it into 3D printed parts. As such, we can connect it to the servo motor to utilise its rotation. I have decided to use 5 motors, each with 11 kilograms of torque, to help move heavy loads. Here is the simplified joint of the 2 degree of freedom arm. This is made in a motion study in Fusion 360. This is in its barest form, and we can build upon this and construct it into an arm we can utilise in real space. Here are the 3D printed components. First we have the base, containing a spot for the servo motor responsible for rotation, and for the top plate to be mounted upon. This was made with heavy double infill to keep the arm from toppling. Next we have the top plate, with spots for 2 motors to allow for double the torque at the main rotational angle, under the most stress and weight. Next we have arm section A. This amateur arm is used to utilise the rotation of the 2 shoulder motors. Furthermore, it is as a housing for the elbow motor. Next we have arm section B, similar to arm section A, but the housing at the end is forward facing, rather than angled towards the left. As such, this allows us to connect it to the claw. The left claw, the right claw, and the cap. These are the 3 components that combined make the working claw, that can grip onto objects. The base of each claw is connected to cogs, allowing 2 servo motors to be connected, as which, when one moves, when connected to a servo motor, the other one will move counterclockwise, resulting in an efficient design only needing 1 motor to move 2 parts. And finally, we have the 5 servo motors and the 5 servo clips. These are the 5 components we are going to use to control and build the robot. Here you can see a quick overview of this. Here we have the diagram of the completed motor from the front view and the top view, each labelled with the correct dimensions. Now I have completed the construction of the motor in Fusion 360, I have made a quick motion study to see the basic motion it can do. For example, I made it to pick up a pen. Now we have seen what it can do in a motion study, I have made an animation showing the full range of what it can do at various angles. Here is my 3D printer. This is printing the components. This printer works by extruding layer upon layer of PLA, which is melted down plastic. As such, it is not able to print over free space, as it is printing upon these layers. This means that when designing my components, I had to consider incorporating and not including overhangs. Here is a live demonstration of the real-life assembled robotic arm. This is moving just like it did in its previous example, and is using very simple code to tell the robot to move to exact positions to pick up an object. Here are the calculations for my inverse kinematics. First, I'll draw out the X and Y graph in green. Next, I'll draw the 2 links of the robotic arm in red. These each have their respective size of 25 cm and 17 cm. Next I drew the hypotenuse in yellow and the X and Y coordinates in blue. Here you can see the calculations for the hypotenuse being x squared plus y squared, all square rooted. Next are the calculations for each angle. Here's the calculation for the first angle in brown. Here's the calculation for the second angle, which is between the 17 centimeters and the hypotenuse. And finally, here is the final angle between x and the hypotenuse, overall resulting in the two angles we need to combine to get the final angle we need for the bottom rotation. Overall, these gives us two angles we can control with the servo motors. Here you can see the live demonstration of the robotic arm moving with these inverse kinematics. This is done by it being controlled through keystrokes. Each time WASD is pressed, the x and y coordinates go up and down, as you can see on the right side of the screen, as the arm moves in these axes. Here is the final code that I will be incorporating my previous inverse kinematics, but also controlling the potentiometers. Here is the libraries, most importantly the mass library. These are the certain functions that we'll be using throughout our code. Next we define some values, next we have some LEDs, next we have some PMW signals that we have incorporated to certain outputs on our nuclear board. Next we have the pins on a nuclear board that will be receiving the potentiometer readings, given here. Here we have the length of the first link and the second link used for the maths later on. Then we have the keystroke char. Then we have the initial position for x and y. And then we have whether the claw is open or closed. Here we have the initialization of the servo motor degrees, 1500 being at 90 degrees or centered. Next we have this interrupt. This interrupt takes any keystroke pressed onto the keyboard and allows it to output certain figures. For example, WSD controls the x and y coordinates when we don't use the potentiometers and we want to test, and G uses the claw to open and close, and 6, 4 and 8 operate the degree of rotation, our third degree of freedom. Here we work out the radians to degrees. Here we convert values into certain ranges. For example, if we have an angle, we need to convert this to a number the servo motor can understand. As such, we use this function. Here we have an averaging function. This takes 10 readings of the potentiometer and divides it by 10 to get an average number to stop jittering. Here we set the period in between each change of the servo motor. Here we initialize this interrupt for the keystrokes. Here we control each width of the PMW signal for the servo motors. Here are the inverse kinematic calculations for both angle 1 and angle 2. First we have the first part of angle 1 plus the second part of angle 1, and then finally the calculations for angle 2. Here are these conversion functions that convert these angles to numbers that the motor can understand. Here are the readings for the potentiometer averaged out. These take these potentiometer readings and convert them into 1 to 1023. Then we convert these values into x and y coordinates. And then here we only allow these x and y coordinates to be changed as long as they're in the specific range of our x and y can be, so it doesn't break the motors. Here we have the smoothing factor to allow it not to jitter. And finally we have the print function that allows us to print certain things in the command to understand what's going on. Finally, this is the overall result of what happens when we combine the potentiometer reading with the inverse kinematics. Here you can see the robot arm drawing a square in free space using the 2 degrees of freedom. The first one is more jittery due to the arm not being bolted down properly, and the second attempt is when I hold the motor down to allow it to draw a more even square.